In this video, we're going to learn about the reactions that happen between acids and bases, which are known as neutralization reactions. So you can tell just by the way that we defined acids and bases that their reactivity is really important. We defined an acid as something that donates a proton to a base, and we defined a base as something that accepts a proton from an acid. So this reactivity, this chemical property about the way acids and bases interact with one another is really fundamental to what makes an acid and what makes a base a base. So a neutralization reaction is really just a reaction between an acid and a base. Sometimes you'll see more specific definitions about what the products are, but really the types of products you produce can vary depending upon the exact structure of your acids and bases. So this is the most general definition, that a neutralization reaction is just when an acid reacts with a base. So based on our definitions of acids and bases, we can be a little bit more specific in that an acid donates a proton or donates H+ to our base. So if we look at a few examples here, I think is going to be the best way to really get this. Let's do acetic acid and sodium hydroxide. So we have to identify what is the acid and what is the base in this reaction to be able to figure out what our products are going to be. So we have that nice clue when we're looking for an acid that we have an H written out in front. So this is our acid in this situation. And specifically, this is a weak acid. So we had our list of 6 strong acids. This is not on that list, but it looks like an acid. So if it's not strong, it must be weak. So we have this H out in front that is our acidic hydrogen. Now, sodium hydroxide, as our other reactant here, is listed on our list of strong bases. Oops, that's the wrong utensil. There we go. So this is a strong base. But what we want to recognize here is that the actual base itself is really just the hydroxide. So the sodium here is actually just a spectator ion. It is not involved in the proton accepting that the base needs to do. So it is the hydroxide, the OH-, that's actually accepting a proton, that's actually functioning as a base. The sodium needs to be there to balance the charge, but it's just a spectator ion in this. So essentially what we're doing is we are donating our acidic hydrogen, so just this one out in front, is going to come over and attach to this OH-, which will leave a negative charged acetate ion here, and the sodium ion, which will be positively charged. So we can write this like a double replacement reaction, where our hydrogen and the cation in our base are essentially just going to swap places. So we will end up with sodium acetate and water as our products here. Being our conjugate base and conjugate acid, respectively. So remember that the acid turns into the conjugate base and the base turns into the conjugate acid after the proton has been transferred from the acid to the base. So this is our kind of molecular equation equivalent. We could also write total ionic or net ionic versions of this as well, which can sometimes be useful. So if we recognize here that sodium is a spectator ion, that in both cases it's part of an aqueous compound, it's not really doing anything, we can write the net ionic version of this. So this was kind of our molecular equation. We can write a net ionic version as well that just removes that spectator ion. So what's actually happening here is that our acetic acid is really reacting with the hydroxide ion, and the sodium doesn't have anything to do with it. So when the acid donates a proton to the hydroxide, this doesn't look like a double replacement anymore because we removed that spectator. We just have the acetic acid losing a proton to become an acetate ion and a hydroxide ion gaining a proton to become water. So let's look at another example. So again, we'll start with kind of a molecular equation approach, where this is going to look very much like a double replacement reaction. So in this one, let's do hydrochloric acid and sodium fluoride. So hydrochloric acid was on our list of strong acids. And I will tell you that sodium fluoride is a weak base. Specifically, it is the fluoride ion that is acting as a base, and the sodium is once again just a spectator. Sodium is pretty much always a spectator. But the fluoride itself functions as a weak base. So with our acid, we have this acidic hydrogen. And for our molecular equation, this is going to be very much like the previous one, that our hydrogen ion and that spectator in our base are going to swap places. And we will end up with NaCl and HF. As our conjugate base and conjugate acid, respectively. So if we want to write the net ionic version of this, is where things get a little bit tricksy. So what we need to recognize here is that our net ionic equation is supposed to represent everything as it actually exists in solution. So for our strong acid, for HCl, we know that in solution, a strong acid is 100% ionized. That means that in a solution of HCl, there isn't really any HCl. All of it has been converted to hydronium. So all strong acids in solution are functionally H3O+. HCl aqueous isn't really a thing, because as soon as it dissolves in water, as soon as it hits that water, all of those HCl molecules donate a proton to the water, generating chloride ions and hydronium. So when we write a net ionic that includes a strong acid, it doesn't actually matter what the strong acid is. It gets replaced with H3O+. It gets replaced with hydronium. So that is a little bit confusing because the water wasn't really part of this reaction directly, but everything is aqueous, so it's around. So functionally speaking, all of our strong acids really exist as H3O+. So we can write them that way. So in this case, our net ionic is actually going to look very different than our molecular equation did. So we recognized that sodium was a spectator ion, so we're going to leave that out. Our chloride is really actually a spectator ion in this also, so that is getting omitted since the acidic component of our strong acid is really functionally the hydronium ion it created in its solution. So our net ionic is now hydronium reacting with fluoride. So when H3O plus donates a proton, it creates water. When fluoride gains a proton, it becomes HF, which is now something that we had in common with our original reaction. So when there's a strong acid involved, net ionics can get a little bit weird for neutralization reactions just because they change so much. But it's the same principles of writing net ionic equations that we want to represent things the way they actually exist in solution. And omit anything that's not actually participating in the reaction. So the chloride ion and the sodium ion here are both actually spectator ions, so those get left out. And what's really happening is just the fluoride ion picking up H plus from hydronium to form HF and water. So let's look at one more that we will try to write the molecular equation and the net ionic equation. For HNO3 reacting with, let's do lithium hydroxide. So why don't you pause here and take a moment and try to predict the products of the molecular equation, and then also write the net ionic equation. So for this one, we need to identify our acid and base. So here we have HNO3, nitric acid, is one of our strong acids. And lithium hydroxide is one of our strong bases. So molecular equation, swap partners, typical kind of double replacement situation here, where lithium is going to end up paired with the nitrate, and H plus OH forms water. So there's our molecular equation. For our net ionic, we need to recognize that in the lithium hydroxide, the lithium is just a spectator ion, so that is going to get left out. That the actual base in here is always going to be the hydroxide in a hydroxide compound. The cation will be a spectator. And then for our strong acid, we need to recognize that this is the same situation we dealt with up here, that it truly exists as H3O+. So in our net ionic equation, we'll represent the nitric acid as H3O+, since that is what is actually present in the solution. And the hydroxide as our base, with the lithium being omitted since it is a spectator. H3O+ is going to lose a proton, which creates water. OH- is going to gain a proton, which creates water. So we would represent this as hydronium and hydroxide reacting to produce two water molecules.